Good morning and welcome back, OChem. I'm so excited. We left with a little bit of a cliffhanger in the last video. Check it out. We kind of left with this reaction. We were looking at a classic E2 example. And when we looked at that E2, we recognized, okay, we've got a base, we've got a solvent that's matching, okay? And with that sodium hydroxide in water, we're in a little baby equilibrium situation. And in order to predict our products, we recognized, all right, our leaving group, our electrophile, and then we marked our beta hydrogens. And when we use a base like sodium hydroxide in water, that matching situation, we end up always getting our most stable product. And we called that thermodynamic control. And our most stable product was our most substituted trans. So in fact, it was this alkene. And then we left our last video with a really awesome question. Well, what if you don't want that product? What if you actually want the least substituted product? How could we make that happen? Well, let's actually kind of list the two reasons we got that most stable product. And we've got our list of solvents and stuff in here. So I am going to scroll down past that. All right. What were the reasons we got our most stable product? So let's write that reaction again. And I'm just going to go ahead and write my sodium hydroxide over the arrow. You can write it either way. Why did we get this one? We had two major reasons. And let's monkey with both of them. So the first one was our actual base. It was kind of a weak base, and that gave us that equilibrium situation and that thermodynamic control. When you have that thermodynamic control, that means your reaction really can go in reverse. Anytime you can sit in a little equilibrium like that, Mother Nature is going to choose the most stable product, because you can simply reform your starting materials and turn right around and make the most stable product. So over time, those thermodynamic controls always give you the most stable product. So if we're going to get the least stable product, we're probably going to have to monkey here. And then second, what determined that most stable product was also the most substituted product. That was our Zetsef's rule. Okay, so we're probably going to have to jack with that a little bit if we want to get the other one. So this, I want to remind us that in an E2, this is a collision. So if you've noticed on this one, actually, this was the harder collision. Aha, so maybe there's something in these two reasons for getting that most stable compound that we could monkey with. And if we could monkey with both of those, maybe we could get the least stable compound. So that's exactly what we're going to do. We're going to use a little bit more modern base, and I'm going to write it over here and show you our reaction conditions. I'm going to take the exact same electrophile and leaving group, and this time I'm going to change the base. Okay, now I'm going to give you the acronyms, and then I'm going to spell them out. And indeed, we are going to get this product instead. So let's mark this as our major product. Let's mark this as our major product. So it's entirely possible. And we are, with this recipe, going to change both of these ideas. So let's scroll down and let's write that mechanism. You know, that's how we describe everything. So let's do it. All right, so let's take that exact same electrophile And I'm going to spell out what LDA is. It is lithium diisopropyl amine. Okay, so check that out. What's the first thing we can compare? Our last base was an OH minus. Now we are looking at an N minus. Okay? So we've now just upped the strength of our base. How do we tell the strength in our bases? We look at that pKa of the conjugate acid. That would be water for our OH minus. Our pKa was around 16. Now what happened when we changed to an amine? Our conjugate acid, we're going to draw it in a minute, is our solvent. Remember, we match them. That is the DIPA. That is our diisopropyl amine. That is on your pKa table. And we're going to notice, let's put it down here, that our pKa is around 36. That is a 20-fold difference. And remember, these are log functions. That is a huge difference. This is a much stronger base. It is really the industry standard for this kind of chemistry. So let's put DIPA as the abbreviation for that diisopropyl amine as our solvent. That's this. Okay. So let's put that in there. And then let's draw the mechanism for why we get this one. Okay, so I'm going to mark this. This is number 1. We just jacked with our reaction conditions. Because of this strength difference between that 16 and 36, this is no longer thermodynamic control. This is so different. This is not an equilibrium really at all. This is straightforward. We're going to call this kinetic control. So our thermodynamic was kind of an equilibrium. Our kinetic, and I'm just going to mark it forward. It is so strong, and it is such a big difference in pKa that over here, let's put our diisopropyl amine, pKa 36, okay? So different that this will now be under kinetic control. And now here's number 2. Our kinetic control tends to be the easiest collision. And we're going to help this along by look at these groups on our diisopropyl amine. They are huge. So not only is this a much stronger base, it is actually huge also. So if we go back to look at our beta hydrogens, which one is the easiest collision for a huge base? Right here. And that is the collision that is going to make our product. Now let me pull up another page, so hang on. Let's get our keyboard up there. Okay, I'm having a raging disaster in this video. I just want to insert a page so I can give us some extra space here. Our page is going to be in between stuff. I really just want my cursor down here. Let's try that again. Yeah, that's just not going to work. I'm going to have to just give it up. There we go. All right, so let's rewrite that so that we can draw our whole mechanism. And what would this look like? Okay, let's have LDA, diisopropyl amine. Okay, let's label everything. This is our base. This is our leaving group. This is our solvent. And this is our alpha or our electrophile carbon. So this whole recipe screams E2, okay? So now that we've got this E2 reaction, and now I'm going to add a little caveat. Remember, the first thing we do is look to compare if we have a nucleophile or a base. This is second order. We have a base. I'm going to add to this size matters. Your sodium hydroxides, your sodium methoxides, any of those R groups here, methyl, ethyl, any of those small bases, O bases like that, they are going to give you your innermost or most stable product. But now our large bases, in fact, we're going to keep it to 1. We are going to use the most common, LDA. We are going to get the least hindered product. So we just added to your list, size matters. So once you figure out you have a base, you have to figure out if you have small or large. All right, so now let's draw our mechanism. When we look at an E2, we take that next step to mark our beta hydrogens. Now we've got a huge base. That huge base is going to prefer the easiest collision. So let's draw our mechanism then. I love our E2s. They happen all at once. Uh-oh. Sorry, y'all, doorbell. This is just a chaos video, isn't it? Okay, so then let's take that base and we are going to react right there at our beta hydrogen. These electrons swing down and we lose our leaving group. And our E2 happens all at once in a nice flow, just like that. And now we just made this alkene. Oh, that came out fluffy. Okay, we just made this alkene. What happened to our base? We still have our isopropyls on there. And we just, what just happened to my pen there? Okay, there we go. We just formed this bond and left behind lithium bromide. Okay, remember this is our matching solvent. That is our conjugate acid to our base, and it's also our solvent. Okay, I love it. So we still have the exact same mechanism with our E2. The only difference when we ramped up our game and we switched to nitrogen instead of oxygen in our base, we now switch to something called kinetic control. Much faster reaction, much stronger base, and our base is huge. So what we did was take this list up here of our thermodynamic control and our most substituted product, and we switched both of those. We took advantage of both. We swapped from thermodynamic control and we ended up with a nice stronger base and gave us kinetic control. And then we took advantage, that most substituted product had the harder collision. So let's use a huge base and select the easier collision. And then you can select that product. So E2s are really powerful. They're used all the time. And by choosing wisely with your base, you can really verify and choose your product. So let's stop this video from here, and then we've got one more video for E2 that we've got one more little bit of sass, and then we're done with our E2s. We'll see you soon.